Hello everybody, my name is Ethan. Welcome back to the channel, where today we are starting a new series on the channel where we're going to be learning about machine learning. This is called the Machine Learning Engineer Career Path. This was the only way that I could find out how to do just a complete machine learning course. If you look at the course, it's going to tell you a little bit about the career path, but typically follows 5 tracks: introduction, the fundamentals, software engineering for MLEs, intermediate machine learning, and then building machine learning pipelines. So if you want to know, there are some prerequisites to this course. It is pretty much going to, I believe, kind of assume that you have a little bit of a role in Python. The reason I'm doing this is because I'd like a machine learning project on my resume, and that is pretty much it. The course itself is supposed to take about 50 hours, and we'll see if we can do that in a good amount of videos. So, without further ado, let's get going on this. It shouldn't be too bad. I'm hoping, at least. We shall see. All right, welcome. Welcome to the Machine Learning Engineer Career Path. No matter what device you're reading this on, odds are that a machine learning engineer behind many of the applications on your device. Here are some examples of applications you know that use machine learning engineering. Netflix's movie recommendation system, Twitter's feed curation, Capital One's credit card fraud alert system, Snapchat's filters, Lyft/Ola's predictive system of on-time arrival. Obviously, many, many more. Safe to say we use machine learning a lot. So what is machine learning? Machine learning is an umbrella term for a set of algorithms that analyze and find patterns in known historical information / training data to make predictions on unknown / new information. What goes into these algorithms? Of course, mathematics. Mathematical functions form the basis of modeling process. Specifically, the fields of probability, linear algebra, and calculus are crucial to building mathematical systems capable of modeling real-world data. So you should have a little bit of a calculus background. Fortunately, I do. I don't know why I'm repping the bright red shirts today, but here we are. Computer science, obviously, as well. Programming languages implement these mathematical models by translating them into a series of executable tasks that a computing machine can implement. Finally, statistics. Fortunately, these are probably my 3 strongest categories in all of school. I obviously go to a university. I guess I shouldn't say obvious. I don't know why I said that, but I mean obvious if you can see that I'm wearing a UW-Madison shirt. Machine learning process is thus not a one-and-done process. Rather, it's iterative. Not unlike the way we humans learn. The capacity of machine learning to simulate human cognition makes it a subfield of artificial intelligence. Okay, what is machine learning engineering? What makes machine learning so ubiquitous today? After all, the practice of collecting and analyzing data isn't new in human history. The answer is quite simple. The advance in hardware and computing technologies are what make machine learning possible. The more training data we have, the better an algorithm can learn its patterns. However, storing and accessing vast amounts of data require robust hardware and pipelines, and running a machine learning algorithm requires lots of computing power and an infrastructure that allows for seamless flow of data between different steps of the algorithm. Here's what the engineering in machine learning engineering comes in. Machine learning engineering concerns itself with designing, building, maintaining, and fine-tuning computational systems that can execute sophisticated machine learning algorithms on large amounts of data. All right, MLE, data scientist, and data engineer, how do these roles differ? If you're scratching your head at this point to what are the differences, here are the differences, right? They're all kind of similar in the data wrangling sense, but data scientists analyze data and generate insights. Data engineers build and monitor data pipelines, and then machine learning, build and deploy machine learning models, right? Perspective AI, machine learning engineer in action. Are huge cat lovers. They want to build an app that solves a problem of abandoned street cats in metropolitan cities as efficiently as possible. Meanwhile, decides on using DigitalOcean, PySpark. Cool. Emily for the win. Kind of, telling you that machine learning is cool, I think, is what we're doing here. This is still kind of just the intro to the course. Maybe I'll make this a separate video, but I don't think so. what will you learn in this career path? The basics of machine learning and software engineering, implementation of machine learning algorithms, how to build machine learning pipelines, how to build end-to-end machine learning app, and how to deploy and maintain machine learning apps, AutoML, and machine learning ops techniques. Okay, so we can start right away. So telling us kind of that. Let's, if you are interested in Codecedemy, I'm not sponsored by them. I simply use their service. I do pay for it. So, yeah. Welcome to Learning Machine Learning Fundamentals. Preview what you will learn in the first machine learning unit. Hi, if you're completely new to data analytics, Python, or Pandas, start with this course, then join us here. So if you don't know what Python is, obviously go look at that. If you don't know what Pandas is, please go look at that as well. Welcome to the Machine Learning Fundamentals unit. This will introduce you to what machine learning is, the data transformations needed to prepare your data for machine learning and modeling, and host a fundamental machine learning. So why did we build this? There we go. What will we learn, though, is more important. Supervised and unsupervised learning basics, feature engineering techniques, implementing supervised learning algorithms like regressors, classifiers, and trees, evaluating the performance of algorithms, implementing unsupervised learning algorithms such as PCA and K-means. Who are my classmates? Learning is social. There's some forums if you want to check that out. Let's get into the meat and potatoes. Come on. All right, here we go. Finally into the meat and potatoes. Here we go. Introduction to machine learning. The year is 2049. New York is overrun by bots and web crawlers. The capabilities of machine learning have reached new heights, and the world as we know it will never be the same. Facial recognition technology that helps users tag and share photos of friends can now tag future friends. Night drones are on the prowl. So, some funny stuff here. Nice little graphic. Let's start it up. What is machine learning? While at IBM, Arthur Samuel developed a program that learned how to play checkers. He called it the field of study that gives computers the ability to learn without being explicitly programmed. What does this mean? As programmers, we often approach problems in a methodical, logic-based way. We try to methodical, logic-based way. We try to determine what our desired output should be, then create proper rules that will transform our inputs into outputs. Machine learning flips the script. We want the program itself to learn the rules that describe our data the best by finding patterns of which we know and applying those patterns to what we don't know. The algorithms are able to learn. Their performance gets better and better with each iteration as it uncovers more hidden trends in the data. Take a look at the timeline on the right. Since Samuel's usage of the term, we have made some astonishing advances in the fields. Boom, boom, boom. Supervised learning. So if you don't know, we're going to be using Python, using NumPy and Pandas. Probably good that you know what some of these are. And it looks like we're also using sklearn and importing linear regression. Okay, supervised learning, regression. Machine learnings can be branched out into the following categories: supervised learning and unsupervised learning. Supervised learning is where data is labeled and the program learns to predict the output from the input data. For instance, a supervised learning algorithm for credit card fraud detection would take the input as a set of record transactions. For each transaction, the program would predict if it's fraudulent or not. Supervised learning problems can be further grouped into regression and classification problems. Regression. In regression problems, we are trying to predict continuous valued output. Examples are: what are the housing price in New York? What are the value of cryptocurrencies? Classification and classification problems, we are trying to predict a discrete number of values. Example are: is this picture a human or a picture of a cyborg? Is this email spam? For a quick preview, here is an example of a regression problem. A real estate company wants to analyze housing costs in New York. They built a linear regression model to predict rent prices from two variables: the square footage of each apartment and the number of burglaries in the apartment's neighborhood during the past year. Run the code to train the model and predict the monthly rent for a 950 square foot apartment in a neighborhood with 2 burglaries in the last year. So we're going to click run, and it's predicting a value of 2,962. Now we're going to change the variable square footage and number of burglaries to different values. Run the code again. How did those changes affect the predicted rent? So we're going to go over here and change the value of square footage. Let's up the value of square footage and lower the value of number of burglaries. We'll run the code again, And in my prediction, yeah, the rent does go up from about $2,900 to about $3,400. And that's obviously, that makes sense in context. If you're getting more square footage in a home, obviously it's going to be more expensive. And if there are less burglaries in the area, people tend to feel a little bit more safe in that area. And we can obviously do the same thing if we lowered it to 400 square feet and did 15 burglaries. It's going to assume that the rent is a lot lower, $1,192 this time. Supervised learning classification. Now that you've seen a regression example, let's look at a classification example. An exclusive nightclub in New York doesn't want to serve robots, but technology has advanced so far that it's hard for bouncers to tell humans from robots just by looking. To help the bouncers, the nightclub created a model that uses the k-nearest neighbors algorithm to distinguish between humans and robots based how long it takes to them to identify, blurry picture, or traffic lights. Run the code to train the model to see whether someone who identifies a picture in 5 seconds can pass as a human. So we have that time to identify picture was 5, and we have this model here. If we change this value to maybe 15, we think you're a robot. So since it took longer to identify if the picture was blurry or the traffic lights there, it ended up thinking it was a robot. All right, so we learned about supervised learning. Let's learn about unsupervised learning. Unsupervised learning is a type of machine learning where the program learns the inherent structure of the data based on unlabeled examples. Clustering is a common unsupervised machine learning approach that finds patterns and structures in unlabeled data by grouping them into clusters. Some examples: social networks clustering topics in their newsfeed, customer sites clustering users for recommendations, search engines to group similar objects in one cluster. For a preview, here's an example of unsupervised learning. A social media platform wants to separate their users into categories based on what type of content they engage with. They've collected 3 pieces of information or data from a sample of users: number of hours per week spent reading posts, number of hours per week spent watching videos, and number of hours per week spent in virtual reality. The company is using an algorithm called the k-means clustering to sort into 3 different groups. Press run to see the clusters. And it has a nice little thing. We have, again, NumPy, pandas, plot from plot clusters. All right, begin our journey. Ding, ding, ding. It was but a dream, and now there's time. Understanding machine learning will help you change this bleak future. Be ready for it. So we learned supervised learning, such as regression and classification, and then unsupervised learning, clustering. Throughout your exploration of machine learning, we hope you gain an understanding how to harness predictive models to do good and enhance human life rather than replace it. So again, looks like we're done there. Let's go over again supervised versus unsupervised. Introduction to the 2 main classes of algorithms in machine learning: supervised learning and unsupervised. As humans, we have many different ways we learn things. The way you learn calculus, for example, it's probably not the same way as you learn to stack blocks. The way you learned the alphabet is wildly different than the way you learned how to tell objects are approaching you or going away from you. The latter, you may even realize you learned at all. Similarly, when we think about making programs that can learn, we have to think about these programs learning in different ways. 2 main ways that we can approach machine learning are supervised learning and unsupervised learning. Both are useful for different situations or kinds of data available. All right, supervised learning. Let's imagine you're first learning about a different genres in music. Your music teacher plays you an indie rock song and says, this is an indie rock song. Then plays you a K-pop song and tells you, this is a K-pop song. Then they play you a techno track and say, this is techno. You go through many, many, many examples of these genres. The next time you're listening to the radio, you hear techno and you may think, this is similar to the 5 techno tracks I heard in class yesterday. This must be techno. Even though the teacher didn't tell you about this techno track, she gave you enough examples of the songs that were techno so you could recognize more examples of it. When we explicitly tell a program what we expect the output to be and let it learn the rules that produce the expected outputs for given inputs, we are performing supervised learning. Right, so known data: strawberry, strawberry, blueberry. Model input data. We have our input data, which is a strawberry, but we don't know it's a strawberry, right? Through our model, it'll learn that this is a strawberry. A common example of this is image classification. Often we want to build systems that will be able to describe a picture. To do so, we normally show a program thousands of examples of pictures with labels that describe them. During this process, the program adjusts its internal parameters. Then, when we show it the next example or new example of a photo with an unknown description, it should be able to produce a reasonable description of the photo. When you complete a caption identifying the images that have cars, you're labeling images. The supervised learning machine can use those pictures you've tagged to make sure the car image predictor is more accurate. Unsupervised learning. Let's say you're an alien who's been observing the meals people eat. You've embedded yourself into the body of an employee at a typical tech startup, and you see people eating breakfast, lunches, and snacks. Over the course of a couple weeks, you surmise that breakfast people most likely eat foods like cereals, bagels, and granola bars, and lunches some sort of vegetable, a protein, and a grain. Snacks are usually a piece of fruit or a handful of nuts. No one explicitly told you what kind of foods to go with each meal, but you learned that from natural observation and put the patterns together, right? So we have an input data here, and we're kind of seeing some patterns perhaps. And so we're going to try and sort that using our model into something that looks a little bit more interesting. In this example, it includes clustering to create segments in a business user's population. In this case, an unsupervised learning algorithm would probably create groups for clusters based on parameters that a human may not even consider. Summary. We've gone over the difference between supervised and unsupervised learning. Supervised learning, just to recap, data is labeled and the program learns to predict the output from the input data. Unsupervised learning, though, is data is unlabeled and the program learns to recognize the inherent structure in the input data. Let's do the introduction to feature learning. Looks like we have some interesting stuff, maybe a project at the end of this. Introduction to feature engineering. Learn about feature engineering and its role in machine learning. Feature engineering is an integral part of building and implementing machine learning models. In this article, you'll learn about what feature engineering is, why you need it, and where it fits in with the machine learning workflow. Additionally, you'll get a brief overview that many data science tools involved in feature engineering and how they assist data scientists in model diagnostics. What is feature engineering? Before we can talk about feature engineering, we have to define what we mean by features. A feature is a measurable property in a data set, and a feature can be used as an input to a machine learning model. One way to think about a feature is as predictor variables that go into model to predict the outcome of a variable. For example, if we want a model that predicts precipitation at a given place in time, we may use temperature, humidity, month, altitude, etc. as inputs. Those are our features. Often when presented with a data set, it might not be clear what features we should use for a specific model, i.e., should we use tree density as an input for a precipitation model? Similarly, in large data sets, there might be too many features to manually decide which features to use. Some features may be highly correlated with one another, and some might not vary much with the outcome variable, and there might be some wrong form to be, and some might be in the wrong form to be a model input, and so on. It is not uncommon that a data scientist might not realize any of this until they have already began diagnosing a model that is performing poorly. Feature engineering is a way to address these challenges. It is an umbrella term for the techniques we use to help make decisions about features in machine learning model implementations. Why do we need feature engineering? To paraphrase Tolstoy, all functional model implementations resemble one another, but every dysfunctional model implementation is dysfunctional in its own way. So there are a lot of different ways that a model implementation can be dysfunctional. One question is, what would make a model implementation functional versus dysfunctional? Consider the following 4 attributes. Performance. We'd like machine learning to perform well on our data. If it is not able to predict the outcome variable to a reasonable degree of accuracy on known data, it would be unwise to use it to predict outcomes on unknown data. Runtime. Suppose a model has an excellent performance but takes a really long time to run. For a data scientist, depending on their available computational resources, such model may be impractical for production. Interpretability. A model is only as good as the insights it helps us glean, love that word, glean from the data. Data scientists are often tasked with finding out what factors drive different outcomes. A well-performing model may not be of much help if it's opaque and unpredictable, or uninterpretable. Generalizability. I think I'm saying that right. We would like our model to generalize well to unseen data. Often data scientists work with streaming data and need their model to be flexible with new and unknown data. Feature engineering can be thought of as a toolkit of techniques to use when model is missing one or more of the above attributes. If we imagine a model diagnostic machine, kind of like a modern version of this one, with meters representing the attributes, feature engineering would be akin to turning the knobs and pushing buttons until we arrive upon a model that meets all of our attributes satisfactorily. This looks like an old-timer kind of thing where we're spinning the dials, perhaps pushing the buttons. Feature engineering in the machine learning workflow. So where does feature engineering fall within the machine learning workflow? Does it go before modeling, after modeling, or alongside modeling? The answer is all the above. Feature engineering is often introduced as an intermediate step between exploratory data analysis and implementing a machine learning algorithm. In reality, these distinctions are fuzzy and the process is not exactly linear. Broadly, we can divide feature engineering techniques into 3 categories. Feature transformation methods. These invoke numerical transformation methods and ways to encode non-numerical variables. These techniques are applied before implementing a machine learning model. They include and are not limited to scaling, binning, logarithmic transformations, hashing, and one-hot encoding. These models typically improve performance, runtime, and interpretability of a model. So there's a couple more here. Looks like the second one is dimensionality reduction methods. Dimensionality of a data set refers to the number of features within a data set, and reducing dimensionality allows for faster runtimes and often better performance. There's an extremely powerful tool in working with data sets with high dimensionality. For example, a 100 feature problem can be reduced to less than 10 modifying features, saving a lot of computational time and resources while maintaining or even improving performance. Feature select methods. Feature select methods are a set of techniques that allow us to choose among the pool of features available. Unlike dimensionality reduction, these retain the features as they are, which makes them highly interpretable. They usually belong to one of 3 categories: filter methods, wrapper methods, embedded methods. Filler methods are statistical methods used to filter out useful features. Filter methods are completely model agnostic, meaning they can be used with any model and are useful sanity checks for a data scientist to carry out before deciding on a model. Here's a brief summary of the feature engineering models we've covered in this article. We're now ready to learn about these in depth. Data transformations. In this module, learn how to prepare your data and feature prior to running a machine learning model. This is a very essential step that, if skipped, can cause some grief down the line. It's usually performed right after or alongside exploratory data analysis, EDA. Why did we build this? Let's take a moment to consider the consequence of not doing data transformations before model implementation. An obvious one might be that the model code errors out. This is still a benign possibility, as it tells you that something is wrong. The more insidious possibility is one where it doesn't cause a problem until much, much later. Multiple diagnoses of poorly performing models later, it might become apparent that the data might need to be transformed in some way at the beginning. Data transformations are thus an irreplaceable step. Let's learn about numerical data transformations such as standardizing, binning, scaling, etc., different ways of encoding categorical and non-numerical data, when and where to apply these methods. If you're familiar with data wrangling, I believe that's what we're going to be doing, kind of getting data in a nice, interesting way, right? So, we've all heard it. A lot goes into getting your data just right for the task you have at hand. Perhaps you are trying to find insight into customer behavior or predicting the best time to send a marketing email. Whatever problem you might be trying to solve, you're probably already spent some time wrangling your data, just getting it right. And now you're at the stage where you need to prepare your data for machine learning. For example, some machine learning models like logistic regression and neural networks can only handle numbers. Then random forest and decision tree models can take both number and text. We will call these features categorical data, but more on that later. We also need to understand the spread of our data, and as some models have a tough time handling data that has extreme outliers. This process is called numerical transformation. When we take our numerical data and change it into another numerical value, this is meant to change the scale of our values or even just adjust the skewness of our data. You may be thinking, we already have our data in numbers. Why would we want to change those? Well, first of all, that's a great question. We'll dive deeper into why we do this throughout this lesson, but to put it simply, we do this to help our model better compare features and, more importantly, improve our model's accuracy and interpretability. We're going to first focus on centering, standard scalar, min and max scalar, binning, and log transformations. To get to know the data frame we'll be using, the dataset has just over 100 responses from customers when they were asked about a recent Starbucks experience. You will soon notice that we have a mix of numerical and categorical data, but we'll focus on the numerical features for this lesson. We have provided you with a CSV file under the name starbuckscustomers.csv, and I've already imported pandas to you and set it to a variable called coffee. So we're going to import the value. So we'll create a variable called coffee, and we'll do pd.read_csv. It might be read_csv. It is going to take me a little bit of time to get back in the swing of things with Python. So if I do make mistakes and errors, please do not blame me. I just did a long course on C#. If you missed that out, you can go check it out. But we can do pd.read_csv, and then we're going to import the file of Starbucks customers.csv. And if we run it, that should be good. Perfect. I think I got the format right. Yeah, there we go. Examine the features in your new data by printing the columns. So this is where it's going to be something interesting. I know if we do coffee.head, what happens? Is that what it wanted me to do? Print df.columns is actually what it wanted me to do. Print coffee.columns. So we're looking at the features, or kind of the variables in our data set. We have spent, nearest Starbucks, age, rate, quality, rate price, rate promo, ambiance, Wi-Fi service, meeting hangout. And now it says look at each feature within your data frame by printing .info. Okay, so it wants us to now print coffee.info. Okay, so it looks like the data types are all integers, which is quite interesting. No strings or anything like that, but it kind of gives us what kind of type it is, right? We got a lot of interesting stuff. Looks like we have 122 entries within the column. 122 each, so that means there was, interestingly, it says that has just over 100 responses. That makes sense because we see 122, and it tells us a little bit more information like memory usage and stuff like that. All right, centering data involves subtracting the mean of a data set from each data point so that the new mean is 0. This process helps us understand how far above or below each of our data points is from the mean. We can look at the nearest Starbucks column by doing something like that. I'm going to move this down a little bit, put that over just a little bit here. And actually, I'm going to move this back up because this is the console. I want to see that a little bit more. We can look at the nearest Starbucks column by using bracket notation. We will find the mean of our feature, create one line of code to center our data, then plot the centered data. Here's what it would look like in Python. So we'll find the mean, and then we'll subtract the mean by taking a distance of that column, and then we'll visualize our new one. Okay, it wants me to use, matplotlib is good stuff. Okay, so let's start by setting age feature to a variable called ages. So we'll do that by doing ages is equal to coffee, bracket notation using the age column. So it says age is not defined, and that's fine. Coffee, it says we can do this, right? Oh, here we go. Again, do not blame me if I'm always a little bit rusty, just a tiny bit. It's helpful to know that both minimum and maximum age in our feature. First create a video, So if we do create a variable called min age, so we'll do min age is equal to coffee age dot min. Can we do dot min? Let's actually use the correct notation though. We could have also done np.min. 13, that makes sense. So that would make sense for our kind of what our data set might look like. A 13-year-old going to Starbucks, perchance. Print max age. And I hate doing that, but I do it all the time. And somebody that's 70 kind of makes sense. Our answer does make sense. So let's now say we want to better understand the spread of our data, so print the difference between min age and max age. Print max age minus min age. We want to find the mean age of our feature to send our data around, so create a variable called mean age. So we'll do that by doing mean age is equal to coffee bracket age dot mean. I was supposed to print the value. Oops. Set the result to a variable called center ages. 27 is the mean age. So now we want to do center our data. So we'll centered ages is equal to coffee age minus mean age. And we probably wanted to print centered ages, which is now it's going to give me an X for this. Perfect. To plot it, it's going to be PLT. What do we want to do? PLT instead of histogram, so hist. I see. And then we have what? Benzo 5 color is equal to green. So I believe if we just put centered ages, it should work. Perfect. Perfect, perfect, perfect. Cool. Standardizing our data. Excellent work with centering the age feature from our data set. We'll now take that concept one step further and discuss standardizing our data. Standardization, also known as the z-score normalization, is when we center our data, then divide it by the standard deviation. Once we do that, our entire data set will now have a mean of 0 and the standard deviation of 1. This allows all of our features to be on the same scale. How cool is that? This step is critical because some machine learning models will treat all features equally regardless of their scale. You'll definitely want to standardize your data in the following situations. Before principal component analysis, before any clustering or distance-based algorithm, think k-means or dbScan. Before KNN, before performing regularization methods like lasso or ridge. If I wanted to see how customers rated quality versus price, I could graph the scatter plot of those two features and easily see customers tend to score those two questions very closely. Notice the darker spots, meaning more data points are lying on top of each other around the 3.0 for rate quality and 3.0 for Rate price as an example. This insight was easy to see since our features are on the same 1 to 5 scale. Now, what happens if I'm working with a feature that is totally different scales, perhaps the customer age and how far they live from Starbucks feature? Let's take a look. Yeah, not that easy to see. So again, z-score, you gotta wanna know a little bit about that and the basics. So look at one feature where customers were asking how close they're nearest Starbucks and follow that formula above. First, we will set our nearest Starbucks feature to its own variable and then find the mean and standard deviation. Then we will quickly standard our list following the formula above. We now have our distance feature standardized. Let's double check by seeing what the mean and standard deviation of our array is. If you don't know what an array is, of course, I don't know. I was wondering why it was highlighted there. So we have distance. We have a column here. We're calling it distance. Then we're going to take the mean of distance. Then we're going to take the standard deviation of distance, and then this will take the find the z-score, right? We now have our distance standardized. Let's double check. So we print type. It's going to say it's a panda score. Now we're going to print the mean and the standard deviation. So this is very, very close to 0. This is very, very close to 1. Our outputs are basically mean equals 0 and standard deviation 1. Let's see what our age feature looks like standardized. So let's set up our variables. Age is equal to coffee age. Oh, never mind. We're saying ages is equal to find the average of your variable. Okay, so we'll start with mean age is equal to numpy.mean. We'll do it this way this time, and then we'll do ages. Find the standard deviation age, so std.dev.age is equal to numpy.std, I believe is the, yep, okay, ages. Standardize our age column, set the variable equal to, and I assume we'll put it right here. It wants it to be ages standardized is equal to ages minus mean age divided by std dev age. It wants me to print the mean and standard deviation. So if we do, we'll do 2 print lines here. We'll do the first one saying numpy.mean ages. I know it's numpy. I just like calling it numpy. And just about 0, just about 1. So very nice. Standardizing our data with sklearn. Now that we understand the mathematics behind a standard scalar, let's quickly implement it with the sklearn library. We'll begin by importing our standard scalar library from sklearn.preprocessing. Import standard scalar. We instantiate the standard scalar by setting it to a variable called scalar, which we can then use to transform our feature. The next step is to reshape our distance array. Standard scalar must take in our array as one column, so we'll reshape our distance array using the reshape -1 method. This numpy method says to take our data and give it back as one column represented in the second value. The -1 asks numpy to figure out the exact number of rows to create based on our data. Pretty cool, right? So we import our stuff here. We set this scalar variable equal to standard scalar method. And then we will create a new reshaped distance variable. We have distance, which I assume is just set equal to, something like that, right? and we reshape it with the -1, distance scalar is equal to scalar.fit transform reshaped distance. Just like we learned in the last lesson, we do this so that our data has a mean of 0 and a standard deviation of 1. Let's print to see how the standard scalar did. Looks pretty good to me. You'll notice that the e -17 at the end of the output for mean, that is our number written in exponential notation, right? So, which basically means 0. You can standardize the age column, the knowledge you just gained. Instantiate standard scalar by creating a variable named scalar. So we will do that by creating that variable named scalar, standard scalar method. Am I spelling it wrong? S-T-A-N. Thought it was scalar. I don't know. Did it in both instances, so that's amazing. Reshape our ages feature and set the result variable name to an ages reshaped is equal to, and it looked like we had some sort of interesting, numpy.array distance, so we'll do that. So we'll do the numpy.array, we'll do ages, and then we'll do the dot reshape with the -1, 1. Next, it wants us to perform a fit transform on our ages reshaped feature to set the results to a variable named ages scaled. So we'll do that. Scaled is equal to fit transform. That method was up here. So we can do that using that scalar, right? So we can do scalar.fit transform. And then we'll put in our ages reshaped. And I did it again with the scalar. I could... Okay, so I'm not wrong. It is an A. So they're spelling scalar weird. Yeah, the same. That's not how you spell it. That's fine, though. I'm not going to hate. Print the mean and standard deviation of your new variable. So we'll do that by doing a couple of different print lines here. We'll do numpy.mean and then add ages scaled. And then another print line, np.std ages scaled. Perfect. All right, let's look at some min-max normalization. Another form of scaling your data is to use min-max normalization process. The name says it all. We find the minimum and maximum data point in our entire set and set each of those to 0 and 1 respectively. Then the rest of the data points will transform to a number between 0 and 1 depending on its distance between the minimum and maximum number. We will find that transform number by taking the data point, subtracting it from the minimum value, and then dividing the value of our maximum minus minimum. Mathematically, a min-max normalization looks like this. So we have math norm, we have our value, we subtract the minimum value, and then we divide it off by the maximum value minus the minimum value. Actually, I don't think I've ever done a min-max normalization, but it makes sense conceptually. The reason we would want to normalize our data is very similar to why we would want to standardize our data, getting everything on the same scale. We did this process to our entire data set, but let's look at the distance to the nearest Starbucks feature. We already know that from earlier in this lesson that our range in this feature is not too large, so it is a good candidate for min-match normalization. We write a function that will perform the mathematics needed to transform the entire column. So first we create the column, set it equal to distance. We'll find the minimum value of find the max, and then do our normalize by using this formula. Excellent. Now if we were to print the unique numbers in normal, here's what we would see. We can see all the numbers are between 0 and 1. Amazing. We'll now work with the spent feature in our data time. Take that column and just set it equal to a new variable called spent. So we're saying it's equal to spent, and it should be equal to coffee with the spent column. Find the maximum value someone spent and set that equal to max spent. So max spent is equal to numpy.max, and then we'll do the spent column. And I assume we're going to do the exact same thing, but instead this time we'll do min spent. Find the difference. So we'll find the difference between max spent and min spent. Set that variable spent range is equal to max spent minus min spent. Now we'll finally normalize our spent column, set the result equal to spent normalized. And we'll do this spent minus min spent divided by spent range. Fine. Finally, it wants us to print spent normalized. Yep. Numbers transformed. Cool. Min-max normalization with sklern. I don't even know how to pronounce that. Is it pronounced sklern? Should we do another lookup? I know we're doing a lot of lookups right now. sklearn. Sklearn. Okay, wait, hold up. Okay. Enough Reddit for today already. Sklearn. It's sklearn, apparently. Okay, happy to see you have a strong understanding how min-max normalization works. Let's try it implementing with the sklearn library. We will start importing our min-max scalar library from sklearn preprocessing, just like we covered in a standard scalar exercise. We will use by instantiating the min-max scalar by setting it a variable called mmscalar, and then we can use it to transform our data. So we've already imported it, which is good. And then we'll do basically the same stuff. Reshape the array and set it to a value called reshaped. So it wants us to do the exact same thing where we do spent reshaped and set it equal to mp.array using the spent column, and then do dot reshape with the same -1 and 1. Let's instantiate the min-max scalar and set it equal to the variable mmscalar. So we'll do that by doing min-max scalar. So we want to do a this basically where we do mmscalar dot wants us to do a fit form with the value of the spent reshaped. Reshaped. Zero and one. Perfect. Binning our data. Binning our data is a process of taking numerical or categorical data and breaking them up into groups. We could decide to bin our data to help capture patterns in noisy data. There isn't a clean and fast rule about how to bin your data, but like so many things in machine learning, you need to be aware of the trade-offs. You want to make sure that your bin ranges aren't small enough that the module is still seeing it as noisy data. You also make sure the bin ranges aren't too large that your model is unable to pick up on any pattern. It is a delicate decision to make and will depend on the data you're working with. Going back to our customer data, looking at the distance feature, here's what the data looks like with a histogram. We can easily see that a lot of customers who completed the survey live fairly close to Starbucks, and our data has a range of 0 to 8 kilometers. I wonder how my data would transform if we were to bin our data in the distance the following way. Distance less than a kilometer, between. First, we'll set the upper boundaries of what we listed above, right? So bins is 0, 1, 3, 5, and 8.1. Now you'll be asking ourselves, why end at 8.1? Why isn't our max value 8? That is true. We have an 8.1 and not 8 because pandas function will use pd.cut. As a parameter, will include the lower bound and excludes the upper bound. So let me show you what I mean. So if we did bin distance is equal to pd.cut dot bins right, left, false, right. Print coffee bin distance will end up getting a lot of 8s. We can see those that who marked 8 kilometers now live in the 5 to 8.1 bucket. The bracket tells us that 5 is included, and the parentheses tells us that 8.1 is excluded. We could write it as an inequality statement like 5 less than equal to distance and less than 1 or 8.1. This allows our customers who mark 8 to belong to the lives greater than 5.1 kilometer bin. Now let's have a look at our newly binned data. So if we do that, we'll end up seeing this bar graph. Print the ages, features, min, and max value. So print numpy dot in ages, and you know what? Numpy dot max ages. I think this works in Python. Yeah, it does. Cool. Based on our results from above, let's set the bin boundaries, stored in a variable called ages bins. And we'll do 12, 20, 30, 40, and 71. Create a new bin column with pd.cut. Name the new column bin ages. Wants to do this interesting cut method here. Is equal to, I see. We want to create a new column in the thing, so we would do coffee. Oh my god, that's so annoying. Do something like this is equal to, and then we want to do PD. I've never actually used this method, so this is new to me. PD.cut coffee, and we want to do it based on ages. So we would do ages bin, and then we have our age bins, and we'll add in this little keyword right is equal to false and see what happens. Holy shit. Is it because I'm using ages here? Probably, if I had to guess, it's just age. Yep. But the first 10 rows of the new column binned ages. If we do print, I want to say it's coffee binned ages dot head 10 Did I do that right? Is it the head method, right? Yeah, head, okay. Plot a bar graph of a new binned data. So we'll do plt dot hist, and then we'll throw in coffee. What does it want us to do here? Oh, wow. Wants us to do coffee binned ages dot value counts. I know I've used value counts before, but it's been a minute. And then we'll do the dot plot kind equal bar. plt dot cool. Natural log transformation. We've covered plenty of transformations. We have one last transformation we need to cover, and that is log transformation. Logarithms are an essential tool in statistical analysis and machine learning preparation. This transformation works well for right-skew data and data with large outliers. After we transform our data, one large benefit is that it will allow us data to be closer to a normal distribution. It also changes the scale, so our data points will drastically reduce the range of values. For example, let's explore a whole new data set from Kaggle around used car prices. Take a look at this historical plot of 100,000 used car odometers. So first we imported pandas. We read in the cars data set. We have a one column called odometer. Graph our odometer readings by bins is equal to 200. Add labels, and we see something like this, right? Xticks equals. This histogram is right skewed, where the majority of our data is located on the left side of our graph. If we were to provide this feature to our machine learning model, we'll see a lot of different calls with odometer readings off on the left of our graph. We'll not see the examples of very high odometer readings. This may cause issues with the model, and it may struggle to pick up on patterns that are within those examples on the right of our histogram. We'll perform a log transformation using NumPy to see how our data will transform. So we'll obviously import NumPy. Log is np log, just finding the log of it, and then actually doing that instead. Rotate the x label so we can read it easily, and then provide title. So we basically use the log function on, and I believe this is just log base 10 function, and then we'll graph it using that and keeping the bins the same. But now our data looks much closer to normal distribution. If we were to look at the sample of 5 different cars with varying odometer readings, let's see how they would look. You know, like very strange looking, right? Like not really a pattern here, but here I can see that the Ultima has a lot lower odometer logged than a Saturn does. If we compare the Ultima with 10,126 miles to the Saturn with 151,687 miles, those two cars have a huge difference in odometer readings. Yet, once we log transform the data, we can see the range from 9.22 to 11.93 is much smaller. Compressing the range of our data can help our model perform better. There's much more to be added about log and transformation, but let's keep in mind that using a log transformation in a machine learning model will require some extra interpretation. For example, if you were to log transform your data to a linear regression model, our independent variable has a multiplication relationship with our dependent variable instead of the usual additive relationship we would have if our data was not log transformed. Keep in mind, just because your data is skewed does not mean that it needs a log transformation or that it's the best answer. You would not want to log transform you have values less than 0. The natural logarithm of a negative number is undefined. If you have left skewed data, that may call for a square or cube transformation, and then you have non-parametric data. All right, let's do it. We've imported all the necessary libraries: NumPy, Pandas, Matplotlib, and Codecedemy library Seaborn. We've imported all the necessary libraries. We need to bring in a file called cars. So let's read in that file using pandas. Pandas dot read car dot p oh sorry, what am I doing? Car is equal to, or cars I should is equal to pd dot read CSV and put in the cars.csv file. So let's read that in. So we want a selling, I hate when that happens. We want a selling price. We're going to call it prices equal to cars and the column of selling price. Now let's look at a histogram of prices to check if it is right skewed. Set your histogram to show 150 bins so we can see more values on our graph. So we're going to do that by doing plt.hist and setting the value equal to prices with bins equaling 150. And I did not do plt.show. So obviously very much so right skewed, right? So looks good. Now I'll perform a log transformation so that the prices and set results in log prices. So we'll do one called log prices, set it equal to numpy.log on prices column. And then we'll plot it by doing the plt.hist, doing log prices, and then do the same thing with that plt.show and see what happens. And it wants me to use bins equals 150 once again. I'm gonna actually take a peek under the hood here and see if I'm actually doing anything wrong. Oh my, it has a lot of semicolons, which I don't use, but what happens if we do this? Looks the exact same. Still looks right skewed, that's why I'm confused. Anyways. Alright, let's do some fun stuff here. Obviously we do something like that. Logarithms are essential tool only when they are right skewed. What NumPy method would you use to perform a logarithmic transformation? .log. Fill in the code to perform a standard scalar. So standard scalar would be standard scalar. You'd want to take your numbers here, subtract the mean, and divide by the standard deviation. Yep. What we expect our mean and standard deviation mean to be a value of 1, standard deviation to be a value of 0. I'm thinking mean 0, standard deviation of 1. Fill in the code to perform a min-max scalar. So we would first take our numbers, which is awesome nums, subtract the minimum value, and then subtract the array range. And then as we center our data, what are we centering around? What metric? Mean. Yeah, centered at 0. All right, perfect quiz. Got all of those questions correct. Hopefully you're following along. Let's continue learning. We're starting a new chapter here. No, we have got 2 more things here and then we'll be done. Encoding categorical variables, encoding categorical variables with Python, introduction, categorical, oh my goodness. That's how you know it's been a long day, guys. Categorical data is data that has more than one category. When working with that type of data, we have 2 types, nominal and ordinal. Nominal data is that has no particular order or hierarchy, and ordinal is basically they have order. We'll be working with a data set of used cars of this article to truly understand and demonstrate how to work with categorical variables and data. Let's explore it and see what types of data we're working with. So when we do this, we see object, int, float, int, and looks like that's it. We can see from the output we have a lot of features that are a data type object. That tells us that those features could be text or a mix of text and numerical variables. For encoding examples, we will explore a few of those object features and transform them to values that could have data frame ready for machine learning. The reason we put time into this level of encoding is that there are many machine learning models that cannot handle text and will only work with numbers. Our data must be encoded into numbers before we begin to train or evaluate a model. Ordinal encoding, we mentioned that ordinal data is data that has an order. Let's take a look at the condition feature from our data frame to perform a value counts to see how many times each label is listed. So value counts, we have excellent, just 186, but new is a little bit less, right? That definitely an example of ordinal data. The condition of the used car can be easily put in the order in the best condition to the cars in the worst. We assume that they follow this hierarchy: excellent, new, like new, good, and then fair. We need to convert these labels into numbers, and we can do so by setting a dictionary, right? Excellent is 5, right? Fair is 1 star, right? Creating column, condition rating is equal to cars condition dot map rating dict. The second approach, we will show how to utilize sklearn, pre-processing in library ordinal encoder. We will follow a similar approach and set our categories as list. And then we will use fit transform the values in our features condition. We will need to make sure that we adhere to the shape requirement of a 2D array. So you'll need to notice the method shape or reshape 1, 1. We'll also notice that this method will not work if your feature has NaN values. Those will need to be addressed prior to running fit transform. So we implement sklearn, pre-processing, and the ordinal encoder, and then we set the encoder variable equal to encoder categories, and then we have our categories, and they're put in a list of lists, right? Let's reshape our data here, and then create a new variable with assigned numbers. So we'll do cars, and we create a new column. We'll put encoder.fitTransform and condition reshaped. Label encoding. Now we can talk about nominal data. We have to approach this type of data differently than what we did with ordinal data. Our color feature has a lot of different labels, but here are the top 5 colors that appear in each data frame. So we have, something that might not actually have an order, right? So color, not going to have an order. Quality, though, you want a higher quality car. That makes sense. To prepare this feature, we need to still convert our text to numbers, so let's just do that. We'll demonstrate 2 different approaches, with the first one showing how to convert the feature from an object type to a categories type. Okay, so we'll say convert feature to category type. So we'll say cars color is equal to cars color as type category. Save the new version of category codes. Not exactly sure what we're doing here. To prepare this feature, we need to convert our text to numbers, right? So we want to first put our text as numbers. Instead of black, white, gray, silver, blue, we want 2, 18, 8, 15, 3. I don't know why, but that's right. Comparing our newly transformed data to the original top 5 list, we can see black was transformed to number 2, white was transformed to 18, and so on. However, we created a problem for ourselves and potentially our model. We can see that blue cars now have a value of 3, and our model will assume that blue has a lower precedence over the black car, whose color has a value of 2. Since blue cars equal 3 and white cars equal 18, our model could actually give white cars 6 times more weight than a blue car, simply because of the way we encoded this feature. To combat this ordinal assumption in our model, we will make a one-hot encode to our nominal data, which we will cover in the next section. This method will not work in your feature NaN from screen. Okay. Perform a label encoder to sure by checking the feature of category type. Make feature to category type. So we'll do that by doing cars make I believe the method was to, or as type, yep, as type. Save new version of category codes. that was up here. It was this .cat.codes, cars, and then it wants us to do the same thing, cars make .cat.codes, print it out, print cars. What I've not done right here. Dot value counts. I mean, that's exactly what I did, but dot as type category. I'm going to move on. One hot encoding is when we create a dummy variable for each value of our categorical feature, and a dummy variable is defined as a numeric variable with two values, 1 and 0. We will continue to talk about our color feature from our used car data set. Looking at this visual below, we can see that we have 10 cars in 4 different colors. In place of the single color column, we create 4 dummy variables, one new column for each color. Then the values that go into that column are binary, indicating that if the car in that row is of the column name 1 or not. Right. The approach is great for our color feature and will allow the model to see each category as its own feature and try to create order between black car and red car. Here's how we implement this in Python. Import pandas, OHE, use pandas.getDummies to create one new column for each color. Then we'll join the columns back into our data frame. pd.get then print the column names. Line 2,800. I feel like I did exactly what it was looking for, but maybe not. It's not liking SUV. Wish you don't get any issues. I don't actually think I added it back to the cars thing, so I would do HE SUV. Yeah. That should be correct. Binary encoding. If we need to use one-hot coding, a lot of categorical variables in turn, blah, 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 binary. We just set it equal to, is that true? If it is, we'll set it to equal to a 1. If it's not, we'll set it equal to a 0. Category encoders and import binary encoder. From category encoders, import binary encoder. Colors equals binary encoder. Calls equals color. Drop invariant equals true. Dot fit transform cars. Hashing. Another option we have is encoding technique called hashing. This process is similar to one-hot encoding, where it will create new binary columns, but within the parameter, you can decide how many features to output. For example, we have 19 different colored cars. If we reduce the hash encoder and set the number of features to equal 5, we definitely have a few colors with the same hash values. You can easily see brown and charcoal colors have the same hash values. Brown 0010, and then what did it say? Coal. Yeah. You may be thinking, when would I use this if I'm going to lose information in my model? We'll see brown and charcoal as the same thing. Well, this could be a solution to your project and data set if you're not interested in assessing the impact of any particular, right? Target encoding. Target encoding is a Bayesian encoder used to transform categorical variables into hash numerical values, and sometimes called the mean encoder. Encoder date time variables. We can make it a time review. Boom. All right, we have a project. All right. Transforming data into features. You are a data scientist at a clothing company and working with a data set of customer reviews. This data set is originally from Kaggle and has a lot of potential for various machine learning purposes. You are tasked with transforming some of these features to make the data more useful for analysis. To do this, you'll have time to practice the following. All right, let's start with some basic exploring. Import your data set, some of the name reviews, save it to the variable called reviews. So we'll create a variable called reviews, set it equal to pd.read.csv under the name reviews.csv. Save that. Next, we want to look at the column names in our data set along with our data types. Do the following: print the column names of your data set. Check your features of a data set by printing info. So we'll print the column names by doing print reviews.columns. And we want to print reviews.info. So looks like we have a total of 5,000 entries, which is quite a lot. And we have a couple of different names: clothing ID, age, review title, review text, recommended, division name, department name, review date, rating, blah, blah, blah. So that's this one and this one. Well, actually not data transformations. Transform the recommended feature. Start by printing the feature's value counts. Look at the counts of recommended. Print. We'll do reviews. Recommended dot value counts, and right now I am for simplicity. Oh wow, C# guys. We'll do this for right now. I didn't actually put it as a method, that's why. There we go. A lot of trues, not a lot of falses, which is obviously something you want to see if it's recommended. Since this is a true-false feature, we want to transform it to 1 for trues, or true, and 0 for false. To do this, create a dictionary called binary dictionary. So we'll do that. Binary dict is equal to the keywords are currently in the recommended feature. So true we'll set to a value of 1, and set false equal to a value of 0. The keys are currently in the recommended values are what you want. 0s and 1s. Using binary dict, transform the recommended column so that now it will be binary. Print the results using value counts to confirm the transformation. Okay, so we want to transform the column by using the binary dictionary. To do this, we're going to do reviews recommended is equal to, what does it want to, I actually want to see how, like this is, oh, it does want the words to be actually true and false. I didn't actually think that it wanted that. And the reason why is because when I did info, oh, recommended is of type bool. Never mind. Since recommended is of type of bool, we can do true or false. So good to always double check that. We can now unput that. And let's transform it. Yeah, so using the map function. Not a function that I've used a whole lot, so I'm not mad at myself for having to look at that one. So we'll do a reviews recommended dot map, and then we'll do the binary dict. Print the transform column now. We now print print reviews the recommended. We should now see that it is, that is good. And using the value counts method, dot value counts, we should now see kind of the exact same thing, right? So we see the exact same thing, but in this case it's true and false, but now it's 1 and 0s, which is what we want. I'm now going to comment this one out, just so we have the one. We kind of always have fresh data towards the top. Let's run through a similar process to transform the rating feature. This is ordinal data, so our transformation should make it more clear again. Start by printing the value counts, check your output, then click the hint. To check your output, click the hint. Oh, I see. Okay, so let's look at the counts of rating. So to do that, we are going to print reviews indexed at rating, and then we'll do dot value counts. And we have a bunch of stuff here. Hated it, not great. Was okay, liked it, loved it, right? So a lot of interesting ratings. We should check it, and that's good. We want to make the following changes to the values, create a dictionary. Again, we're going to do a very similar thing here where we have another dictionary, set it equal to the dictionary of loved it is going to be set equal to 5. We want liked it to be set to the value of 4. We want was okay to be set to the value of 3. We want not great to be set to the value of 2. And then finally we want hated it set to the value of 1. So now we'll transform the rating column so it has those things. So we're going to do something very similar, where we're now going to go again and do print out reviews, or not print out, sorry, but change the rating column. We're going to set it equal to reviews dot, or not, my goodness, rating. That's how you know this video has gone on for way too long. Dot map, and then we'll do the rating dict. And now I am going to get rid of, we have printed this one out already, and we'll save that, just keeping this information up top. We'll now print out, print the value of reviews, rating dot value counts. And we'll see that it looks like that. We can check it probably and see that it, oh, no, I guess not. Now let's transform the department name feature. This process will begin a little bit differently, but start by printing the value counts of the feature. Use pandas get dummies to one hot encode our feature. Attach the results back to the original data frame and print the column names to see. So get the number of categories in a feature. We'll transform printing the value counts method. So we'll do print. This looks good, so I am going to just comment this out now, so we're not cluttering our screen. We'll print the value of reviews with the, what do we want? Category or department name feature. Department name feature dot value underscore counts. Okay, tops, dresses, bottoms, intimates, jacket, trend, cool. It's of type int 64, good to know. Everything is good to know. We're going to use the pandas.getDummies method on the thing, so we're going to have it equal to one hot encode. Set it equal to pd.getDummies for the column reviews and department name. Oh, and call it wants to be called one hot actually instead. That's what we did. Join the results from one hot back to our original data frame. So we can do that by doing reviews dot join and put in one hot. I believe that's, yep. And then print all the new column names. So now we should have join the results from one hot back to the original data frame. There's only one beer left. Ah, we have to actually save it to the new one. Now we should see them. Yep. Let's make one more feature transformation. Transform the review date feature to the date time. That's the one I really skipped over. So, not good, guys. So it says PD to date time df column. So reviews, review date is equal to pd.to date time, and then we'll do reviews, and we want the new column to be there's only one beer left. Review date. Review date into a datetime feature. The datetime 64. Finally, the scale our data. We notice that we have a wider range of numbers thus far, so it's best to put everything on the same scale. Let's get into our data frame and have numerical values. If you get stuck, click the hint. Let's get our data frame to only have numerical features we created. There's only one beer left. We have the final step. We have to transfer reader data. I noticed that we have a wide range of numbers thus far, so it's best to put everything on the same scale. Let's get our data frame to only have the numerical features we created. There's only one beer left. Oh, it literally just tells me use the following line of code. That's always nice. Use the set index method. Reviews is equal to reviews dot set index column. There's only one beer left. So to do the fit transform, we have to do standard scalar. Is everything implemented so far? It actually is. So we can just call this scalar is equal to standard scalar. So first we'll have to reshape our data. So to do that, we'll call this reshaped reviews, set it equal to PD. Is it a panda method? I want to say it's not. Standard scalar, fit transform. Create a standard scalar and then use fit transform and reviews. Your code should be similar. Oh, it doesn't want me to actually reshape the data. So we'll just do what it said to do, right? Yeah, so that was right. It just wants me to do scalar. I guess it doesn't want that. It wants scalar dot fit transform reviews. Congratulations, you completed this transformation project. Cool. All right, guys. So that is going to do it for this chapter. We are about halfway through machine learning fundamentals. We went through the entire introduction, so we did a lot today. It's going to be a way longer video than normal. If you did enjoy the video, please be sure to give it a like, subscribe, and I'll see you. And Mr. DMX Monkey back there is going to also see it in the next one. Peace out.